So let's move ahead. So the next important concept for you all is to understand properties of electric field lines, and we will also discuss electric flux in this particular video. So like I told you before, field lines are imaginary lines so drawn that the tangent to them gives the direction of force on positive charge placed at that point. That means suppose there is a charge here, and if you place a positive charge at this particular point, the direction of the force on the positive charge will give you the direction of the field lines. Second thing is, already we have discussed that positive charges are sources for field lines and negative charge is a sink for field lines. Then again, a very important concept is that suppose there is a charge here, suppose let us say there is a positive charge here, we will see that the field lines will be moving radially out. Okay, if you see the field lines moving radially out, suppose I take a unit cross section here, okay, and suppose I take the same cross section a little away. So do you understand that the number of field lines will be reducing? Yeah, so the density of field lines would also indicate the strength of the electric field at that point. So if the field lines are dense, the electric field at that point will be dense. If the field lines are scarce or far away from each other, then the electric field at that point will be weaker. Okay. The most important property which is very often asked in your exams is the fact that if you have two field lines will never intersect. So why will two field lines never intersect? So the reason why two field lines will never intersect is, let's look at this point of intersection. So we already defined that a field line is drawn such that the tangent there gives you the direction of force on positive charge. So at this particular point, if you consider this field line, the tangent is like this. For this, if you consider this field line, the tangent is like this. Now if you keep a positive charge, will it move this way or will it move this way? It can't. Okay, there has to be only one direction in which it can move. So because there is only one direction in which it can move, two field lines can never intersect. Okay. So the simple straightforward question they ask you for 2 marks is, why do electric field lines not intersect? So this is the basic reason why the electric field lines don't intersect. Okay. So I hope you are able to understand these properties of electric field lines. So then let's move on. So the next part we will look at what is electric flux, and then we will try to understand electric flux better. Okay, so now let's look at the next part, that is electric flux. Definition wise, electric flux is the number of field lines cutting through a given cross section. Suppose this is a region where there is a uniform electric field. So if there is a uniform electric field, the electric field lines will all be parallel to each other. If you have a charge, let's say if you have a charge here, the electric field lines are not parallel to each other. So this is not a uniform field, this is a non-uniform field. This is a uniform field. So suppose you have a uniform field this way, suppose we are talking of a cross-sectional area of this kind. So you see that there are 1, 2, 3, 4, 5 field lines which are going to cut through this cross-sectional area. So the electric flux is 5. Okay. So electric flux is defined as the number of field lines cutting through a given cross-sectional area. So in this case, the number of field lines will be, the flux will be 5. But there is a problem. The problem is, till now whenever we have seen anything in electrostatics, we have never said how many field lines to draw. Okay, so what I am trying to tell is, suppose you have 1 coulomb charge here and you have shown it via 4 field lines. If you have 10 coulombs also, you can show it via 10 field lines. There is no rule saying that because it is 10 times larger than this, we have to draw 40 field lines. Okay, so the number of field lines which we need to draw for a given charge has not been defined. So even though in literature we say that electric flux is the number of field lines cutting through a given cross-sectional area, mathematically it cannot be explained this way. So mathematically the way electric flux is defined as, it is defined as E dot A. That is, it is the dot product. Electric field is the dot product of, electric flux is the dot product of E and A. E for electric field, A for area. So electric flux is the dot product. Because it is a dot product, electric flux is a scalar quantity. Also electric field is force per unit charge. So it will have a dimension m l t power minus 2, this is force divided by at. So it will become m l a power minus 1 t power minus 1. Now that we are multiplying it with L squared, area has a dimension L squared. So the dimensions of electric flux will be m L cubed a power minus 1 t power minus 1. Remember, for all the quantities that you are learning in the 12th standard, it is important for you to understand what the dimensions are, because several times direct questions come both in the NEET exam and in the board exam. What is the dimension for electric flux? So we should be able to say that clearly and easily as to what the dimensions are. Okay. So I hope you are able to understand what electric flux is. I will repeat again, it is the number of field lines which are cutting through a given cross sectional area. Because the number of field lines is not defined mathematically, electric flux is equal to E dot A. So let us see these two questions. So there is a question here which says, suppose there is a charge capital Q here. I have drawn two concentric spheres, one has a radius r and the other has a radius 2r. Suppose the flux through the first surface is S1 and the flux through the second surface S2 are given here. The question is, what is the ratio of the flux on the two surfaces? The question is, what is the ratio of the electric flux on the two surfaces? Now, what have we said? Electric flux is equal to E dot A. So if it is E dot A, if you see area of a sphere will be 4 pi r squared. So very clearly, if you see, the area of S1 will be 4 pi r squared, the area of S2 will be 4 pi 2r the whole squared. So when I remove the brackets, it will become 16 pi r squared. So you may be tempted to say that it is equal to E into 4 pi r squared divided by E into 16 pi r squared. So you can cancel off everything and then say it is equal to 1:4. You may be tempted to say it is 1:4, but this is not the answer. Why? Because again we have to go back to the definition. Definition of electric flux is number of field lines cutting through the given cross sectional area. So if you have field lines here, let me just change the color so that we will understand it better. So I will make it yellow. So if we have the field lines here, so you see any field line which is cutting through 1 is also cutting through 2, and any field line which cuts through 2 has to cut 1. So field lines are continuous lines, so they cannot be, they don't terminate here and there, so they only terminate at negative charge and they originate at positive charge. So in this case, the field line, whatever is cutting surface 1 will also be cutting surface 2. So the ratio of the electric flux will be 1:1. Okay, and it need not be spherical. Suppose there is one which is a sphere and suppose other outside it I draw a cube. Even now the flux is going to be the same, because every field line which cuts through the outer cube has to cut through the sphere and then come, right. So the ratio is always going to be 1:1. Okay, so I hope you are able to get it. Okay, let us look at the next question here. So there is a region here where there is an electric field of strength E and there is a cube. So there is a cube of dimension A cross A cross A. So the question is, what is the electric flux through the cube? So the electric flux through the cube is 0. So I will explain to you how. Not just necessarily a cube. Suppose this is a region with a electric field. A three-dimensional object of any dimension, any shape, will have a net flux equal to 0. Okay, so that is a very important law which we will learn later. There will be a net flux only if there is a charge inside. If there is no charge inside, there will be no flux. Anyway, let me explain to you how. So this is a sphere, this is a cube. So now let us look at the different faces of the cube. So first thing is, understand that area is a vector quantity and not a scalar quantity. So now the big question is, what is the direction of the area vector? So suppose I have a plane of this kind. This is A here, the length, this is the breadth. The area is the cross product of A and B. So the area vector is perpendicular to the plane carrying the two vectors A and B. So I repeat, the area vector is perpendicular to the plane carrying the two vectors. So here I have one face. So perpendicular to that face is this. Here I have another face. Perpendicular to that is this. Now for both of these faces, flux is E dot A. So the angle between the electric field and the area vector is 90. So cos 90 is 0. So the flux on this and this will be 0. Yeah. Similarly, there are these two side walls. Again, the perpendicular will be outwards and on the other side. So the flux on those two also will be equal to 0. That is, on this wall and the opposite wall, the flux will be 0. There will be some flux on this wall and there will be some flux on the opposite to this wall, which is there here. So let's call this 1 and let's call this 2. For this particular surface, the area vector will be outside. So E dot A will be equal to EA cos theta. So that will be cos 180. For this one, the area vector will be perpendicular to this. For this, the flux will be EA cos 0. So as you know, cos 180 is minus 1. Now because cos 180 is minus 1, these two will cancel each other out and you will get that the net flux is equal to 0. So the flux through this given cube will be equal to 0. Okay. So in this context, I can explain to you another question quickly. Suppose there is an electric field here and we have a plane of this kind. Let's say that this angle is equal to 60 degrees. So if this angle here is 60 degrees, the perpendicular to that, so the perpendicular to that will be 30 degrees to the given surface here. So if it is 30 degrees to the given surface here, the angle between the area vector and the electric field vector will not be 60, but it will be 30. I hope you are able to understand. See, this is the plane of the area. This is the perpendicular. So this is the area vector and we are talking about the electric field. This angle is given to you as 60 degrees. But when you do E dot A, this should be the angle between the electric field and the area vector. So here the electric field and the area vector will be at 30 degrees and not 60 degrees as given in the question. So the answer should be EA cos 30, and cos 30 is equal to root 3 by 2. So the answer should be root 3 by 2 EA. Okay. So these kind of questions come quite often in the NEET paper where they are just trying to test your basic concepts. Whether you know what is the area vector and what is the electric field. The fact that the area vector is perpendicular to the electric field. Okay. So I hope you are able to get this.